We have seen in the parts 1, 2, 3, and 4 of ARIMA modeling and forecasting how to fit an ARIMA model, how to write it in polynomial form, how to expand it to obtain the forecasting model as a familiar looking regression model. And we have left the last step to determine whether the model that we estimate is stationary and invertible. That is very important in ARIMA modeling, that we have the AR model that we fit to the difference time series and the MA model that we fit to the difference time series, if we difference, that they are stationary and invertible. So in this lesson, we are going to learn to determine whether the AR part of the ARIMA model fit to the difference time series is stationary, and whether the MA part of the model is invertible. And we are going to use a polyroot function in R to determine that. So why do we need that? All AR models that are non-stationary are not useful for forecasting, and that's why we do that. And MA models that are non-invertible are also not useful for forecasting. So that means that they don't satisfy some mathematical models that stochastic dynamic models had to satisfy in order to forecast and finite forecasts instead of giving us infinite values that are unrealistic. So it's important that we make sure that our models, when using ARIMA, are both non-stationary if they are AR and invertible if they have MA. Okay, so all MA models by definition are stationary, and we saw that when we checked their theoretical ACF, when we studied the theory of stochastic processes, we saw that MA models after lag Q have autocorrelation equals 0, and that happens after the order of the model. So if it's some MA of order 1, after lag 2 and 3 and 4 on are have autocorrelation 0. Then if the order is of order 2, then after lag 2, that means lag 3, 4, 5, R sub 3, R sub 4, R sub 5 will be non-significant, right? AR models, on the other hand, are invertible. Invertible means that you can express a model as an infinite, as an AR model with infinite number of terms. AR models by nature are invertible, but they could be non-stationary. And we saw that when we looked at ACFs of some AR models that had significant autocorrelations up to a very large number of lags. So they start looking somehow like non-stationary processes. So we need to make sure that the model we are fitting to our time series after differencing, the one that we estimate, is stationary, okay, before we proceed to forecast. So we can determine those conditions if we write the model in Backshift polynomial form, which is what we have been practicing in the last 2 lectures. So I remind you again from previous lectures and previous lessons, and that we're in this lecture series, that the Backshift polynomial is just this little bit that we put in front of our time series, and that B means that we're lagging the series 1 time. So B of y50 equals y49. And we saw this in earlier lectures, so I will not spend much time on it. B to the power k means that we are lagging the time series k times. So B12 of y50 is y at time 38. Okay, now with regular difference at time series using the regular difference operator, as mathematically speaking, and the regular difference operator applied to a time series yt is yt minus 1. And we can write the difference operator as a Backshift polynomial. So the difference operator is actually a Backshift polynomial of order 1. The seasonal difference in operator depends on the kind of seasonality that we have, sorry. So if it's monthly, we seasonally difference 12 times, not 12 times, but up to like 12. And if it's quarterly, like 4. So the difference, seasonal difference in operator means it's this inverted triangle sub L means that 1 minus b to the power L, and b to the power L is just log L, right? So 1 minus BL, so the difference operator at log L YT will be the polynomial 1 minus b to the L YT, and that will be YT minus L. So this notation is important because what happens is that we summarize the differencing in polynomial form. And that's the preferred form of expressing ARIMA models. So the trend that we do, if we do regular differencing, we write that for a transform series or a non-transform series. We usually do that as and express that in polynomial form as 1 minus b by the amount of differencing. If we difference regular difference once, the little d will be 1. And typically we will want to just do that once. But if we are forced to do it more than once, then the little d might be bigger than 1. Then the seasonal differencing is multiplicative to the regular differencing. Almost all modeling in ARIMA modeling is multiplicative. So this, if we do seasonal differencing, we're multiplying that to the polynomial of the regular differencing. Okay, that's a very common expression for the trend part. And this will appear every time that we do differencing and express the estimated model in polynomial form. So all MA models are stationary, we said, but we need to check their invertibility. Suppose we have a time series process that is a moving average of order Q. So that means the model is YT equal WT plus beta 1 WT minus 1, and the WT terms are white noise. Okay, and we express this model. Let's say we didn't difference or anything, ARIMA 00Q. Then the process can be expressed in terms of the Backshift operator as a polynomial in the Backshift operator, right? So what we do is just take out the W term and then realize that the Backshift operator lacks the variable, and just write this polynomial instead of WT plus beta 1 WT minus 1 plus beta 2 WT minus 2, we can write 1 plus beta 1b plus beta 2b squared plus plus beta kb to the k, and multiply everything by WT, with the understanding that the b, which is the Backshift, will apply the lagging to the WT. So if the roots of this polynomial, are outside the unit circle, okay, we say that the process is invertible. And that means that it can be expressed as a stationary or process of infinite order. And I hope you ignore these blue letters here. They should have been removed, okay? So suppose, so what we are trying to say when we are saying that if the model is invertible, we're trying to say, for example, if it was an MA1, we're trying to say that it can be written as an infinite series, okay, as an AR model of infinite number of terms. This will go on forever and forever. And that would require that in the MA1, the parameter beta in absolute value is less than 1, could be negative or positive, okay? So let's go now to the AR models. AR models are always invertible. Of course, they can always be expressed as an AR model of infinite number of terms by just substituting each y's of t minus 1 and so on. But we need to check their stationarity. So suppose we have an AR process, okay, an AR model for their P, a model in which we did not difference. Then the model case can be expressed as YT equal alpha 1 YT minus 1 plus alpha 2 YT minus 2, and so on. But you can also write it in polynomial form. So we can write it as 1 minus alpha 1 b to the 1 minus alpha 2 b to the 2, and then multiply by YT. So notice in this case, we are moving the polynomial to the left-hand side of the equal sign. That's different from the W, from the moving average model. And we leave only the WT to the right. So if the roots of this polynomial in B are outside the unit circle, okay, so in absolute value, they're larger than 1, then we say that the process is stationary. So it's worth seeing a couple of examples. Suppose this example is from Copperware's textbook, which I have recommended you to read because it's free and it's in our library. So suppose we have xt equals 3, 2, xt minus 1. So this is an ARMA model, right? So this is ARMA. There is no differencing done here. So this is ARMA with parameters AR2. There is no differencing done. And there is MA1, okay? So this is ARIMA, and there is no seasonal par, okay? So this is ARIMA 0201 and 000 in the notation, in the ARIMA notation. So this is ARIMA, okay? So we write the model in polynomial form. We bring the AR part, So AR part and trend part are always going to be on the left-hand side, to the left-hand side, and we have the MA part on the right-hand side. Okay. So what we need to make sure is that we have the AR polynomial on the right-hand side with the right signs, and in the polynomial is in the backshift operator. And then we are trying to find the roots for B, okay? So what we are saying is and then we are going to use polyroots because that's otherwise is mathematically complicated to find the roots of this polynomial. Well, you could do it, right? Because this one is just quadratic, but the module of the polyroot of the roots, okay? So we are going to look at the absolute value, and this gives us the roots 1 and 2. So one condition for this process to be stationary, for the AR part to be stationary, is that the roots are outside the unit circle. The absolute value is bigger than 1. So since one of the roots is 1, the process is not stationary. Okay. So let's do now the roots of the of this polynomial. Okay. So this the roots of the MA polynomial. For the MA polynomial, for the MA process to be invertible, MA process is always stationary, but for it to be invertible, the roots also have to be modulus larger than 1. And we do the polyroot command in R and find a module to get the absolute value. And we find that the root is 2, and therefore the process is invertible. Okay, so the MA part is invertible, but the AR part is non-stationary. So this will not be a good model to forecast. Let's do another example. So this would be a model in which we have 2 terms for ARIMA. So it's ARIMA of order AR2 for the regular part. Because how do I know it's the regular part? Because it's the small lags, okay? Regular part, low lags, okay? R sub case at low case, okay? And then we have the MA part of the model. So we did not difference here. We don't have terms that are without coefficients, right? All the terms have a coefficient estimated, so they are not trend terms. And then we have a regular MA of order 1, and then we don't have any seasonal part here. So we have to convert this model to a polynomial. So we bring the AR part, to the left, okay? And then so first we did xt minus 710 xt minus 1 plus 110 xt minus 2, right? And then equals wt minus 3/2 wt minus 1. And then we take out, then from here we go to this step, okay? And our AR part on the left-hand side and the MA part to the right-hand side, and we check the roots of the polynomials. So the roots of this polynomial using polyroot, okay? So we will use the mod of polyroot of C1 minus 710, 710, 110. Okay, and that gives us 2 and 5, which is larger than 1, since the absolute value of the roots is larger than 1. The AR model is stationary, the AR part, okay? And now we need to check that the MA part is invertible. So we do module of polyroot of C1 minus 3/2, and that gives us a root 0.66, which is the less than 1. So that means this process is non-invertible. So this will not be a good model for forecasting. And here is another example. This a model in which we have, in this model, we have ARIMA. So we have an AR part that has order 2. We don't have any terms that have no coefficients, so therefore we did not difference. Then we have an MA part that is of order 2. We don't have any seasonal differencing or seasonal model fitting, right? And what we do is that we bring again, so we have xt minus 3/2 xt minus 1 plus 1/2 xt minus 2. And then we put the wt minus 1/3 wt minus 1 plus 1/6 wt minus 2. Okay, so that's the next step. And then that brings us to this polynomial notation, okay, using the Backshift polynomial. And then we can check the roots. We have one root of 1 for this polynomial, for the AR polynomial. So the process is non-stationary. She's one of the roots of the AR part, okay, is 1. And then the root of this MA part is 2.4, which is larger than 1, 2 and 4, okay? And so the process is invertible. The roots are 2 and 4, so the process is invertible. But because one of the AR part is non-stationary, we don't use this model for, okay? So let's go back to what we fitted for our rooms data set. Remember, we fitted this model in past lessons. So we ended up with this model. This was the seasonal differencing, right? And then this is the AR model. And this is the MA model for the regular, AR for the regular part. And then MA for the regular part. And this is the MA for the seasonal part. And we look at each polynomial separately. So we look at the module of the polynomial polyroot for the AR. So the AR non-seasonal part polynomial, and we find the roots are very close to 1, but they're larger than 1. So we say that the AR model is stationary. Now we check the invertibility of the MA terms. So we look at the invertibility of the regular MA model, and that gives us a root of 1.71. So that checks the regular MA part is invertible, and the regular seasonal part, and the MA seasonal part gives us also a root in absolute value larger than 1, so that's also invertible. So therefore, this is how you do it to check stationarity and invertibility. So we saw with an example all the steps of ARIMA modeling. Actually, this will be incorrect. So what we saw, how to find, sorry about that, how to find the whether the AR model is stationary and whether an MA model is invertible. Okay, and we use the polyroot function for that, okay? So very important that you do that before you proceed for forecasting. When we have our data, these are the steps that we are going to have to do in addition to all the other steps that we described in previous lessons. I hope you enjoyed it, and I will stop the recording now.